Hello everyone and welcome back to my SPH tutorial. In this episode, I'm going to talk about kernels in general and about the famous WPoly kernel used for calculating densities. In the last episode, we did a lot of theory, like what a fluid is, the equation behind it, and the loop of the 5 steps I showed, and yeah, the whole simulation basically. Today we start building the actual thing, and we're going to write the really first piece of code for that. A quick reminder of the loop. We have our particles, and the first thing we do each frame is ask for every particle, how crowded is it, and that's the density. Once a particle knows how packed it is, everything else will follow. Pressure, forces, motion, and so on. So density is step 1, and that's where we headed. So how do you measure crowding? One simple idea is to count the neighbors inside of some radius. That works, but it's rough. A particle sitting very close to you should count for much more than one that's barely inside the radius, right? And counting treats them the same. There's another problem. The count jumps. A neighbor moves from 1 pixel past the edge, and it goes from counting fully to counting 0. That sudden jump would show up as jitter in the fluid. What we actually want is a smooth distance-weighted count. Close neighbors count a lot, far ones count a little, and it fades to nothing at the edges. Instead of dropping off suddenly, right? And that weighting is exactly what a kernel is doing. Okay, so here's the kernel. In the papers, you always see it written as a capital W as a function of two things. R, the distance between two particles, and H, the smoothing radius, how far the kernel reaches. Why W? Well, the papers don't really say, but an easy way to remember is it's a weighting function, because that's its job basically. It takes the distance and gives you back a weight. Look at the shape. It's a bell curve. It's tallest at the distance 0, or right where the neighbor is closest to you, and it falls off smoothly as the neighbor gets further away until it reaches exactly 0 at H. Past H, it's 0. The last point is really important. It means any particle further than h away contributes nothing, so we can ignore it completely. That's called compact support, and it's what makes this fast. Instead of every particle interacting with every other particle, each one only looks at its few neighbors inside its radius. And this is the one we are building today. It is called Poly 6. Poly because it's a polynomial, and 6 because of the power that appears when you expand it. It's the standard kernel for density, and you can see why from the curve. Smooth, rounded at the top, going gently from to 0 at h, and it's the distance weighting we just described, written as a real formula. One quick aside, there's a 3D version of the Poly 6 as well. It is the same shape. The only thing that changes is the constant out front. So because we are in 2D, we are normalizing over an area, and in 3D, we will normalize over a volume. We are building a 2D simulation, so we use the 2D constant, the one on the screen. The 2D version of this kernel we will use is coming from the paper called SPH-based shallow water simulation. The link is in the video description if you're interested. And if you do a 3D simulation, you of course have to use the 3D poly. And this is coming from the paper Particle-Based Fluid Simulation for Interactive Applications. We will also follow this paper for the whole tutorial. But we have to switch the kernels for the 2D case. So if you do a 3D version, use the one in the paper. Link is, as I said, in the video description. Now, Poly 6 isn't the only kernel. There's a whole family of them, and each one is suited to a different job. Let me show you the most important other one. It is called Spiky. Look at the difference near the center. At small distances, Poly 6, the one we are building today, is rounded there. It flattens out at the top, right? And Spiky comes to a sharp point at 0, which is where the name is coming from. Here's why that matters. And it's also previews something we will do later. When we get to pressure forces, we are going to need the slope of the kernel, so how fast it changes. Poly 6 slope goes flat right at the center, which is a problem. Two particles that get very close would barely push apart, and they would clump together. Spiky doesn't have that problem. It stays steep near zero, so it pushes hard when particles get too close. So poly 6 is for density and Spiky is for pressure. We are not writing Spiky today though, we will add it in the episode where we need it, so when we do pressure stuff. But I wanted you to see why one kernel isn't enough. Okay, so let's settle on what H is. It is this moving radius because it comes up constantly, and yeah, that's why we go over that again. H is the reach of a particle, the radius of that circle going around. Anything inside interacts with it, anything outside is ignored. If H is too small, the particle can't sense its neighbors. If it's too big, every particle interacts with every other one, and the simulation slows down. Its value we will tune later. Well, yeah, it's a volume we will tune later. And looking ahead, later in the series, when we build a grid to find neighbors quickly, we will set the grid's cell size equal to H. That's a convenience choice. It means a particle only has to check its own cell and the 8 cells around it. Depends on how you build the grid. There's also the way to build just 4 cells, but we will do the 8 cells. Yeah, a 3x3 block, basically. So to be sure, it has found everyone within H. We don't have that grid yet for now. Finding neighbors would just be like brute force. But keep H in mind because it lines up with the grid nicely. And for everyone who wants to code along the episodes, this is my repository for my book, and we will also use the same code. The link is in the video description. For this tutorial, we will start with a specific branch. You can just download the starting code. If you go to the repository and go to branches right here, you see there are 71 branches, quite a lot. And you can, if you search by the branch name, or maybe you're lucky and you find it already here, we will start with chapter 2.0 SPH setup. So if we search for it, it should appear right there too. There we go. We had it just here, and then you can either clone it, or you can just download it as a zip file, for example, and put it somewhere in your folder and start from there. And you don't need to download anything else. If you are, if you have any problems, or I don't know, you encounter some mistakes, you can always check the branches. I will link them always in the video description, and you can build from there too and compare the code. Okay, so let's jump to the implementation. First, a quick tour of the project. This time I'm not gonna do an extra episode for setting up the project. I did this already quite a lot in my other tutorials too. If you're interested, you can take a look there. Instead, I'm gonna use or a already set up project. I'm just gonna walk you through what it is and all these kind of things. And yeah, I think we can start with the main HTML file. This is just the entry point. It loads all our scripts, right? Creates the simulation and runs the loop. And every frame, it clears the canvas, updates and draws. You also see a few commented out lines here. This is like the other more advanced methods from the branch of the code from my book. So we will not take a look at those methods. Maybe at some point later. but not in this series, so you can ignore those. And yeah, then we have the vector2.js file. This is our small 2D math library. Add, subtract, scale, length, normalize, dot product, nothing, SPH specific, just the vector math we will use throughout. It's finished, so we won't change anything. Then we have draw utils. This is just like a drawing helper to draw points, draw some text, and that's all. Then we have the SPH particle.js. This is a single particle. It has position, velocity, density, pressure, mass, force, and a color. Right now, density, pressure, and force are all 0. So they are kind of placeholders we will fill in as the series goes on. And I think all the variables are kind of explanationary. Yeah, and then we have the SPH simulation.js. This is the simulation class where all the logic goes in. Currently in the constructor we make a block of particles, about 500 of them, and we lay them out in a grid and space them apart. Update is empty right now, so nothing is moving currently, and we draw the points in the draw method. Yeah, and then you see a square of blue particles. Then we have the fluid hashgrid.js. This one is empty for now. This is our fast neighbor search I mentioned previously, and it stays empty until later. So don't worry that it's included, but empty. And then we have the kernel.js file. Here's the one we are filling in today. Okay, so let's start implementing the polykernel. We see the formulation can be a little bit weird. I think it's still understandable. We need to have a method. I call it just like in the paper poly. I dropped the 6. We can write 6 there. I think it is still quite understandable. In the paper, they say R and L. R, we will take the R2. This is our distance between the particle. And they use L instead of H. You find those two notations quite often. They mean the same thing. L and H is the interaction radius. I will use H for now. Then we can have the bracket. And then we have the condition we see in the formula. So we need to compute the L squared and the R squared, or in our case, for L we use H, so H squared. So let's do the if, for example. First, there's an, it says in the formula if R is bigger or equal than 0, and if R is smaller than H. They use smaller or equal than H, or in this case L, right? They write L instead of H. I use just smaller than H, that's fine too. Then we calculate L squared or H squared and R squared. So we will do this now. Let's say H2, I will call it H2 is equal to H times H, and then the R2 is equal to R times R, right? So this is quite easy. And then the else, of course, you can see there, otherwise it's 0. So that means we just return 0, okay? So that's everything. And then we can use the H squared and the R squared to compute the value. You see in front of the bracket there's a division 4 divided by p times L power of 8. We can do this or write this like this. We return 4, right? We do the division first. 4 divided by math.p or pi times math.pow. And here we say h to the power of 8. And then we have this fraction, right? And then we can multiply this stuff by saying, okay, we multiply it again. We have here again a math.pow. So we write math.pow. And then we say h2 minus r2 and then to the power of 3. And this is the whole WPoly 6 thing. And yeah, this is already everything for the kernel. And we are done with this part for now. Okay, and this is it for this episode. In the next episode, we will actually code the density function so we can estimate or calculate all the densities about all particles. Thank you very much for watching, and I hope to see you in the next episode. Have a nice day, and bye-bye.